Welcome to the solutions to the Regents Physics Dynamics problem set, problems number 33 through 35. Let's start by reading 33 and seeing what we have to work with here. A car moving at 10 meters per second, this would be its initial velocity, crashes into a barrier and stops, so its final velocity would be 0 in 0.050 seconds. That would be time. There is a 20 kilogram child, mass, in the car. Assume the child's velocity is changed by the same amount as the car's in the same time period. A, what is the average force exerted on the child? Capital F. What is the mass of the object whose weight equals the average force calculated in part A? What they're wanting us to do here is convert this force found in A to a mass. In C, if 1 kilogram weighs 2.2 pounds, could you lift the mass in part B with your arm? So then they want us to take this mass, calculated in B, convert it back to a weight, except they want us to do it in pounds so that you can relate to the answer. And then D, they ask us to, according to our results, explain whether it would be better for the infant to be in a restraint system rather than held on your lap. More to come on that. All right, so for A, was the average force exerted on the child? We're going to use the impulse momentum theorem here, where the impulse, F times t, causes a change in momentum, and that momentum is caused by a change in velocity. So F times t equals m delta v. Substituting in what we know, we're looking for F. Our time is 0.050 seconds. Our mass of the child is 20 kilograms. And the change in velocity is final 0 minus initial 10 meters per second. The force exerted on the child here would be negative 4,000 newtons to two digits, negative 4.0 times 10 to the third newtons. Okay, just for reference, this 20 kilogram child in our measurement system weighs 44 pounds. Okay, so that's a 44-pound child undergoing 4,000 newtons of force during that collision. Also, for perspective here, think about how fast 10 meters per second is. 27 meters per second would be 60 miles per hour. 13.5 meters per second would be 30 miles per hour. So this is in the neighborhood of 25-ish miles per hour. So from 25 miles per hour to 0, still quite a bit of force, even though that's not that great of a velocity. All right, now we take this force and convert it to mass as requested here in B. We do a quick little W equals mg. Our 4,000 newtons of force divided by 9.81 meters per second squared gives us a mass equivalent of that force of 408 kilograms. C now asks us to take that amount of kilograms and convert it to pounds so that we can relate to that amount of force. So 408 kilograms, at a quick little dimensional analysis, 2.2 pounds is the weight of 1 kilogram. We put the kilograms in the denominator to cancel kilograms. We end up multiplying 408 times 2.2 and we get 898 pounds. Essentially what has done here for B and C is that they have converted this force in newtons to force in pounds that we can relate to, and that's 898 pounds. Could you lift that much weight? Could you apply 898 pounds of force to prevent this from happening? Obviously the answer is no. So it would be much more advisable to have a proper infant restraint, an infant in a proper restraint system, rather than hold this child on your lap, because you would have to exert 898 pounds of force to prevent the child from crashing into the dashboard or going through the windshield. You obviously are not going to be able to do that, especially with just your arm. All right, let's move on to number 34. Marble A of mass 5 grams moves at a speed of 20 centimeters per second. It collides with the second marble B of mass 10 grams moving at 10 centimeters per second in the same direction. After the collision, marble A continues at a speed of 8 centimeters in the same direction. Draw before and after diagram, and what is the velocity of marble B after collision? For our before and after diagram, before we have marble A 5 grams moving at 20 that catches up to and hits marble B of 10 grams moving at 10 centimeters per second in the same direction. Afterwards, we're told that marble A continues at a speed in that same direction at 8 centimeters per second, and we're asked for the speed, the final speed of marble B. Afterwards, it is not, these objects aren't stuck together, so we have to treat them separately, just like we do beforehand. So we start with our conservation momentum statement, P before equals P after. Notice in this problem that I've not converted grams to kilograms, and I've not converted centimeters per second to meters per second. That's one of the nice things about conservation momentum, as long as your units are consistent throughout the problem, that you don't need to do that. If you think about it, what you would have to do is take each of these gram numbers and divide by 1,000. Well, you're going to end up doing that to every term in the equation, so it ends up being a wash in the end anyway. Same thing with centimeters per second to meters per second. Whatever your conversion factor is, ends up happening to the same to every single term, so you don't need to do that because it'll end up washing out in the end. We just have to remember that when we're done, we have to have our units correctly expressed, whatever they are. So we have our 5 grams times our 20 centimeters per second is the momentum of marble A, plus 10 grams times 10 centimeters per second is our momentum of marble B beforehand, equals 5 grams times 8 centimeters per second for marble A, plus 10 grams times the marble B's final velocity, which is what we're trying to find. We multiply each term together. We add these two together on the left-hand side. We subtract the 5 times 8 from the right-hand side, and then we divide our answer by 10. And when we do that, we should get a final velocity of 16 centimeters per second. Next, 35. 2 students on roller skates stand face to face, then push each other away. One student has a mass of 90 kilograms and the other has a mass of 60 kilograms. Draw a before and after diagram of this situation. Find the ratio of the students' velocities just after their hands lose contact. Which student has the greater speed and which student pushed harder? All right, we start with the before diagram here. I'm going to put the less massive student on the left and the more massive student on the right. And before they push each other, they're both at rest. Afterwards, the 60 kilogram student would move to the left, and the 90 kilogram student would move to the right. I've called the velocity of the left-hand less massive student VW, and I've called the velocity afterwards of the more massive student going to the right VL. We start with our conservation momentum statement, P before equals P after. There is no momentum beforehand because neither one of these objects is moving. And then we have 60 kilograms times VW minus 90 kilograms times VL because it's moving in the opposite direction. Adding the 90 VL to the left-hand side, we have 90 VL equals 60 VW. B wants the ratio of the students' velocities, so we need to get a ratio of the speeds here. So what I did was I did a ratio of VL to VW. So I divided both sides by VW and then both sides by 90. So VL over VW gives us 60 over 90, which is a ratio of 2 to 3. All right, now, which student has the greater speed? Well, clearly the less massive student on the left, if you look at the ratio here, VL to VW is 2 to 3. So VW has the greater speed, which makes sense because they're less massive. The more massive student would have a lower speed, so that when we cancel out their momentum, their momenta end up being 0 after collision. And then D, which student pushed harder? This is a neat little question from earlier, a review earlier, and that's Newton's third law. For every action force, there is an equal and opposite reaction force. So the answer is neither, that they pushed equally on each other because of Newton's third law. All right, that'll do it for this particular set of problems. You'll have one more conservation of momentum problem, number 36, which you will do in class tomorrow.